Hello, welcome back to the first course in general physics. And in this lecture, we will still be talking about the systems of thermodynamic systems, and we will be focusing our attention on the application of the basic principles of thermodynamics, such as the first law of thermodynamics and the second law of thermodynamics, and the definition of the thermodynamic processes as applied to another type of engines that operate between two temperature reservoirs. And we will talk about specifically the refrigerators. The refrigerators are essentially engines that are operating in reverse. So it will be our subject for this lecture, which is the last lecture in this topic and in this course. So we still are talking about the basic principles of thermodynamics as applied to real-world engines and refrigerators. And as I said, this will be the lecture that is concerned with refrigerators. What is a refrigerator? A refrigerator is a machine or a device that also exchanges heat with the environment, and it cools down a compartment. But as we mentioned in the beginning of the discussion of the principles of entropy, entropy does not allow you to extract heat from a cold place and throw it into a hot place. So in that sense, the refrigerator is operated by another motor or another engine, sort of, in order to provide work to this machine. And that work will facilitate the extraction of heat from the cold reservoir, which is the food compartment inside the refrigerator, and throwing it to the surrounding, like to the kitchen environment, for example. Because otherwise, without this work to facilitate such a process or a series of processes, we will never be able to extract thermal energy from this compartment and throw it continuously to the environment of the kitchen. It is never possible to extract naturally heat from a colder place and throw it into a hotter place. So that's why we need work. We need to supply this machine with some work coming from another engine or another motor. So that's how this machine works. It operates depending on work that runs it, and thus it extracts heat from the low temperature compartment or reservoir and transfers heat into an exhaust heat into the surroundings. That is the general principle or definition of a refrigerator. Air conditioners and heat pumps are essentially refrigerators. It just depends on what are the low temperature reservoir and the high temperature reservoir. For example, in the case of a conditioner, of an air conditioner, the low temperature reservoir is the room that we are cooling, and the high temperature reservoir is outside the room. So the conditioner, the air conditioner, takes thermal heat from inside the room and throws it into the outside, and thus continuously cooling the room. It operates again between two reservoirs, the room that's being cooled and the outside, the surrounding outside the room, which are at a hotter temperature. And again, in order to operate this air conditioner, we need to supply work to the conditioner. We need to run it using another engine or motor and supply work. Heat pumps are also similar engines, but for a heat pump, we are concerned in heating a compartment, and thus we extract heat from a low temperature reservoir, which is the outside of the room that is being heated, and we introduce this heat, pump it into the room that we are heating. So the lower temperature reservoir is the outside in this case, in the case of heat pumps, and the high temperature reservoir is the room that we need to heat. But in each case, we extract energy. In each of these three cases, we just extract energy from a lower temperature reservoir or compartment and throw some exhaust heat, thermal heat, into a higher temperature reservoir in each of these three cases. So essentially, they are similar, and they are sort of like the heat engines that we discussed in the last lecture, but operating in reverse in a way. This is a diagram that illustrates the operation of the refrigerator. This diagram shows that the refrigerator, right at the center of it, at the heart of it, we have the working substance. And the working substance, which is like the gas in the refrigerator, goes through a cycle, a cyclical process, starting from an initial state and going back to the same initial state. And this cyclical process is run by work that is supplied to the refrigerator by an external agent. So we use work to run this substance and to run these cycles. And in running these cycles, heat is extracted from the lower temperature reservoir, which is the food compartment in the case of refrigerators. And this amount of heat Q sub C that is extracted, it makes the compartment colder. In the process, as a result of the process, an exhaust heat Q sub H is thrown away to the surrounding environment at a higher temperature T sub H, which is in the case of the refrigerator in the kitchen, the high temperature reservoir is the kitchen environment itself. This is the operation of the refrigerator in principle, and as we see, we could view it as an engine operating in reverse. If we reverse the arrows, if we reverse all the arrows, then we will get just the heat engine that we have discussed in the previous lecture. And as we discussed in the previous lecture, we are concerned when we are dealing with machines that we construct for a special purpose. We are concerned with the efficiency, because we would like to construct a machine that would give us as much of the benefits that we are seeking from the construction of such a machine, as much as possible, as much benefits as possible, and as low cost, at a low cost, as low as possible. So we would like to also be concerned about the efficiency of such machines, and as usual, we define the efficiency, or we measure the efficiency in the usual form by the ratio of what we get, the benefit that we get, divided by what we pay for, divided by the cost, in a way. That's a measure of the efficiency. It's not really the efficiency which ranges from 0 to 100%, or from 0 to a unit, but it's some sort of a measure for the efficiency. And this measure of the efficiency is called the coefficient of performance, K, and this coefficient of performance, K, is defined in the usual manner as Q sub C divided by W. And notice that this definition follows the same logic that we have talked about, that it is the benefit that we are seeking, what we want Q sub C, the amount of heat extracted from the food compartment, or from the low temperature reservoir, which is the food compartment, the inside of the refrigerator. We want this Q sub C to be as big as possible, and the work, which is the energy that we pay for, that is work that we supply the refrigerator with, we want this to be as small as possible, as much as Q sub C divided by W is greater, then we call the efficiency, or the coefficient of performance of the machine to be higher, and the machine is thus a better machine. Again, the work can be replaced by the amount of heat absorbed per cycle of the working substance, as we have done in the case of discussing the heat engines. And in an ideal refrigerator, if we assume that all processes in this refrigerator are reversible processes, in order not to waste any more energy, if all of these processes are reversible and we have an ideal refrigerator, then as usual, if we follow the cycle of a refrigerator, then the work done during the loop of consisting of the 4 strokes or of the cyclic process that is performed during the operation of the working substance, if the area inside this loop is the work done, which is a positive quantity, then this area, the work done, is equal to Q sub H minus Q sub C. And this is a resultant of the fact that during this cyclical process, the internal energy change is 0, and from the first law of thermodynamics, the net heat absorbed during this cyclical process is equal to the work done, and thus the work is equal to the net heat absorbed, which is simply Q sub H minus Q sub C. And thus the coefficient of performance has a new shape now, a new form, given by K is equal to Q sub C divided by the difference Q sub H minus Q sub C. And I have introduced the absolute symbols for each Q in order to make sure that we are taking into consideration only the magnitude, because the sign is taken into consideration right away in the equation. It is explicitly written in the equation. And again, the ideal refrigerator is simply an ideal engine operating in reverse, as we mentioned. If we looked at the diagram of the refrigerator and reverse the arrows for the operation, we get the ideal Carnot heat engine. If that's the case, then we again obtain that QH over QC is simply TH over TC, and replacing these terms in the coefficient of performance. You know, if we go back to the coefficient for performance, which is Q sub C over Q sub H minus Q sub C, if we divide over and above, if we divide by Q sub H, then and then multiply by T sub C, we get this equation. The coefficient of performance is given in terms of the temperatures of the lower temperature reservoir and the higher temperature reservoir. And as we mentioned before, it is a useful formula. It's much more useful than the previous one, because in the previous formula we are dealing with amounts of heat that is extracted or absorbed from or thrown away from the low temperature compartment, and the heat that is thrown away to the environment. We are dealing with the amount of heat that is taken away from the lower temperature compartment and thrown away to the environment, and per cycle of the operation of the working gas. And that is a quantity that is difficult to measure in principle, and that is why we use this formula, which is applicable only for ideal refrigerators. That is the condition, in fact. This is applicable only for the case of ideal refrigerators. Typical values of the coefficient of performance are such that, for example, for an air conditioner, a regular air conditioner, the coefficient of performance, K, is about 2.5, around that number. And for a house refrigerator, the typical value for K is about 5. Those are just typical numbers for such machines. And from the numbers, we notice that even though this formula gives a measure of the efficiency, which is the coefficient of performance, it is still not an efficiency. It's not a real efficiency term, because the efficiency runs usually from 0 to 1. There is nothing that is more efficient than 100%. But it's a measure of the performance, which is somehow correlated with efficiency of the machines. Now, we will be discussing the concept of a perfect refrigerator. As we mentioned in the context of discussing the heat engines, the dream of engineers and inventors is to construct a machine with perfect performance. And in the case of refrigerators, a perfect refrigerator will operate without work, without the need for an external work. If the work is to operate the machine is zero, that means we are dealing with a refrigerator that simply extracts heat from a colder place, from a colder reservoir, which is the food compartment in the refrigerator, and throws that heat into a hot reservoir, which is the environment of the kitchen. Or similarly, it's like an air conditioner that is operating without electricity, without the need for work. It's a machine that once you put it in there, it just simply sucks the heat from the room that you are in, cooling it down, and throws that machine outside, throws that energy outside without the need for any electricity or for any work done. This is beautiful. This is perfect to have. But we know that this is impossible. And as we discussed in the context of the direction preference of processes in nature, we demonstrated by examples that such engines do not exist, which would simply extract heat energy from a colder place and throw it to a hotter place or reservoir. It is impossible. It's against nature. But let's look at this problem closer in the case of refrigerators. Let's assume for the time being that we can construct a perfect refrigerator which takes heat from a colder reservoir and transfers that heat into the hotter reservoir without any work done, without the need for work. If we assume that we have such a machine, this refrigerator the principle of operation of this refrigerator is shown in this diagram. This diagram shows simply an engine that is operating again between two temperatures, a cold or a low temperature reservoir at T sub C and a hot temperature reservoir at T sub H, with the working substance at the core of the machine working in cycles, in strokes, making cycles. And if this machine sucks energy, heat energy of an amount Q, and transfer it to the hot or the high temperature reservoir, the same amount of heat Q, then we will have a perfect refrigerator without the need for doing any work, and thus such a machine would cool any place without costing us any penny. A refrigerator would be cooling our food without plugging it in. An air conditioner would be able to provide us with comfortable environment inside a room in a hot summer day without costing us any energy, without plugging the conditioner into the electricity. And similarly, we will be able to heat with such machines. We will be able to heat our homes and our cars and everywhere without costing us any penny. That is a real dream. Now, let's have a closer look at this problem, because we have a feeling that it is impossible to achieve this goal. It is impossible to just simply extract energy, heat energy, from a colder place and throwing it into the hotter place. We have that feeling, and let's look at this problem more carefully, taking into consideration the operation of the machine and the basic principles of thermodynamics. So, during the operation of the working substance during a cycle, the entropy of the working substance does not change, because the working substance starts from an initial state and goes back to this initial state by the end of the cycle. However, the entropy of each reservoir changes. Thus, the cold reservoir, which is the inside of the refrigerator in the case of discussing refrigerators, the cold reservoir will lose energy Q sub C, and thus the change in its entropy is simply minus the magnitude of Q sub C divided by the temperature T sub C. However, the high temperature reservoir, which is the kitchen in our example, will be provided by some heat energy Q sub H, and thus the entropy of the kitchen, of the environment, will increase by the amount of Q sub H divided by the temperature of that environment. Then, if we take a closed system, since we apply the second law of thermodynamics to a closed system, we will be concerned with a closed system, and the closed system consists of the low temperature reservoir, the high temperature reservoir, and the working substance. For a closed system, the total change in entropy is the change in entropy of these three members of the system. The change in entropy of the working substance is zero, because it simply goes back to its initial state. However, each cycle, the entropy of the cold temperature reservoir is reduced as heat is extracted, and the high temperature reservoir, its change in entropy is increased. The entropy increases as we add heat to it. And in the case of a perfect refrigerator, the work is zero, which means that Q sub C and Q sub H are equal in magnitudes. Thus, in this case, for our total closed system in a perfect refrigerator, we will have the total change in the entropy of the system is simply minus Q sub C, minus Q, which is Q sub C, it is equal to Q, divided by T sub C plus Q divided by T sub H. In this formula, each of the values Q sub C and Q sub H are equal in magnitude, but one of them is negative, indicating the loss of heat, and one of them is positive, indicating the absorption of heat by the different reservoirs. So this is the total change. This would be the total change of the entropy of the total closed system, consisting of the working substance, the gas inside the refrigerator, the compartment of the refrigerator, and the environment, the high temperature reservoir, which is the kitchen in our example. And since the temperature of the high temperature reservoir is bigger than the temperature of the cold temperature reservoir, T sub H is greater than T sub C. Since this statement is correct, we conclude that Q divided by T sub C is greater than Q divided by T sub H, and it is negative in sign, so the sum minus Q divided by T sub C plus Q divided by T sub H, which gives delta S, is negative. And thus, we will obtain a result that tells us for a perfect refrigerator, the total entropy of the system consisting of the refrigerator, the high temperature reservoir, the low temperature reservoir, and the working substance, this total system, it experiences a decrease in the entropy per cycle, every cycle. And that result does violate the second law of thermodynamics. This is not allowed. And the violation of the second law of thermodynamics tells us that it is impossible to have such a machine. And in fact, it is impossible. We cannot construct such machines. And this violation of this second law of thermodynamics, by the fact that we cannot construct a perfect refrigerator, leads to the necessity to rewrite the second law of thermodynamics in a yet new form, which illustrates this point clearly. And this new statement for the second law of thermodynamics reads, there is no series of processes that is possible in nature whose sole or total result is simply the transfer of heat from a reservoir at a given temperature to another reservoir at a higher temperature. This series of processes are not possible in nature. And this is the modified, or this is an alternative form of the second law of thermodynamics. So far, we have arrived at three different statements for the second law of thermodynamics. One of them relevant to the general processes, and one of them relevant to the fact that it is impossible to construct a perfect heat engine, and one of them is relevant to the fact that it is impossible to construct a perfect refrigerator. But those three statements are equivalent. It is nice to mention at this point that nuclear power plants are heat engines. They provide us with, they extract energy from the core, the nuclear core, the high temperature reservoir, and they provide us with work that provides us with electrical energy by the end. But these plants throw so much energy into the surroundings, like rivers and seas, that is much more than the energy that they produce and we can benefit from. And the efficiency of such machines, such as this power plant in this slide, they do not exceed in real life 30% or so. At this point, let me touch on an example of the heat engines and refrigerators and see how we can apply the basic principles of thermodynamics to look into problems and solve such problems. As an example, let me take this problem, and this figure shows the to the right a refrigerator operating between a cold temperature reservoir T4 and a high temperature reservoir T3, thus extracting heat Q sub 4 from the low temperature reservoir and exhausting Q3 to the high temperature reservoir, operated by work W. This work is provided to the refrigerator by a heat engine, and the heat engine is operating between a high temperature reservoir T sub 1 and a low temperature reservoir T sub 2, and where it extracts energy Q sub 1 from the high temperature reservoir and exhausts heat energy Q sub 2 into the low temperature reservoir. And both the refrigerator and the heat engine are assumed to be ideal machines. Let's assume that they are ideal machines. Now, as for the ratios of the heats, for example, Q3 to Q4 or Q4 to Q3, we can find these ratios in terms of the temperatures T4 and T3 from the fact that this machine is ideal, as we have discussed a little while ago in this lecture. And also, as for the ratio Q2 over Q1, the ratio of these heats in the engine, also we have the means of calculating these ratios, taking into consideration the fact that this engine also is an ideal engine. However, if we are concerned with another question, what is the ratio between Q3 and Q1? The heat that is exhausted to the environment by the refrigerator divided by the heat that we pay for, that we use in order to operate the engine, which in turn operates the refrigerator. In this case, we don't have a direct answer for Q3 divided by Q1. So how do we solve such a problem and obtain a result or a solution for the ratio Q3 divided by Q1 as an example? In this way, we will be using the basic principles depending on what we have learned in this lecture. We know from the ideal engine that the ratio Q1 divided by T1 is equal to Q2 divided by T2. That is coming from the ideal engine. And the second relation that we know is Q3 divided by T3 is equal to Q4 divided by T4, and that is coming from the ideal refrigerator. Also, we know that in each cycle of both either the refrigerator or the engine, in each cycle, the amount of work done is simply the difference in heat or the net heat absorbed. So from the engine, W is equal to Q1 minus Q2. And from the refrigerator, the same W, because the same W produced by the engine is the same W that is operating the refrigerator. This same amount of work is equal to Q3 minus Q4. So these are known parameters and known quantities, and now we move on to the solution of the problem, and we rearrange the terms, and we obtain Q3 is equal to Q1 minus Q2 plus Q4. It might look convenient from this one relation on the top that we divide by Q1 in order to get whatever we need. If we divide by Q1, we get in the left-hand side Q3 over Q1, which is the quantity that we need. In the right-hand side, what do we have? We have Q1 over Q1, which is okay. It is 1. We have Q2 over Q1, which is also okay. It is T2 over T1, simply from the ideal engine equation. But we have another quantity, which is Q4 over Q1. And Q4 is coming from the refrigerator, and Q1 is coming from the engine. And we don't have any direct result for that. So what do is we multiply Q4 and we divide it by Q3, by the same number, Q3. Multiply and divide by the same thing. It's just like doing nothing. And then rearrange the terms. Then on the left-hand side, we will get Q3 multiplied by, in parentheses, 1 minus Q4 over Q3. And on the right-hand side equals Q1 minus Q2. Now, if we divide by Q1, everything can be solved, and we have an answer. Thus, divide all the equation all through by Q1, we will get the result. Q3 over Q1 is equal to 1 minus T2 over T1, all divided by 1 minus T4 over T3. And thus, this ratio of the heat exhausted to the atmosphere or to the environment by the refrigerator divided by the heat that is provided by us and paid for to operate the engine and consequently the refrigerator itself, that ratio is given in terms of the temperatures, and these temperatures can be easily measured or somehow can be measured, and we can have an answer for this problem. And at this point, I would like to end this lecture, and the end of this course altogether. I wish you good luck, and thank you for your attention.